Hi, good morning. Good morning to everyone. This is Shiv Kumar Shah and welcome to the Gate Mentor Academy.com. So okay, आज हम लोग एक नया प्रॉपर्टी डिस्कस करेंगे that is called your surface tension and it's a very important property and a fluid properties. So the surface tension is defined as force per unit length, or that is also called cohesive force per unit length. And the surface tension is indicated by sigma is equal to F by L, and it's a Newton. The second important point, that surface tension exists due to cohesive force. It's not adhesive force, it's a cohesive force. The surface tension exists due to cohesive force. And the third point, the surface tension always acts on the circumference. Surface tension acts on the circumference. And the fourth point is tangent drawn at any point in the film. That tangent will be always a normal to the line. So the tangent is always normal to the line drawn. Line drawn from the center of the film. Center of the film. And the next important property is a surface area. Surface energy. It's not surface area, surface energy. So that one will indicate by ST. So before that, I have assumed that three types of films are there. That is one is a film is a completely submerged in the liquid, and these are the liquids are there. And this is the free surface of a liquid. So this is the completely submerged film is there, and this film is a stable film. Why? Because of equal force is acting in equal direction at an equal length. So that's why the resultant of these forces will be zero. Resultant will be zero. It means the film will be stable. Same way, this is a partially stable film is there because half of the portion are submerged and half of the portion are above the free surface of the liquid. So I can say that these forces are acting downward. It means the total resultant forces are acting downward, and this is here partially stable. But if you assume that this film, some portions are above the free surface of liquid and more than half portion are below the free surface of a liquid. So I can say that here the total resultant force will act downward. Hence, I can say that this type of film is an unstable film. Unstable film. The next important properties is their surface energy. The very important surface energy. The surface energy is defined as surface tension into a surface area. Surface tension into surface area, that is a sigma into A, indicate that surface energy. Or in another way, we can say that the amount of energy required to break the big area into a smaller area, or to break the particle into a smaller number of particles is called here surface energy. So I can say that the energy required to break the film into a smaller number of film is called here surface energy. Surface energy. So like if you assume that, let us consider this is the big film is there, and this film radius is r, and this film is divided into a 64 smaller number of particle or film. Then how much the surface energy required to break the big particle or big film into a smaller film, into a 64 smaller film. So first of all, I will try to find out the radius of a smaller film. If you are able to find out the radius, you can find out the surface energy. So to find out the radius here, equate the volume, like whatever the volume of the big particle, that must be equal to 64 into volume of a smaller particle, because there is a total 64 molecules are a smaller particle. The volume of bigger particle will equal to, it's a 4/3 pi r cube, because this is in a spherical shape, and 64 into 4/3 pi into a small r whole cube. This two will get cancelled here. So the small r, we can say that it's a r cube by 64. So the r will be equal to r/4. So the smaller radius, I got it here, it's the capital R/4. So here we can find out the surface energy, and the surface energy will be surface tension into area. So what is the area of the sphere? It's a 4 pi r square. It's a sigma into 4 pi, and the r value is a r/4 ka all square. So it will be equal to sigma into 4 pi into r square divided by 16. It will be 4 for the 16. That will be here pi sigma r square by 4. So this is the amount of energy required to break into a 64 a smaller number of particles. So this type of questions they are asking in GATE. It's a very important for GATE point of view. Please remember the concept, how to find out the radius and how to find out the surface energy. Sometimes they'll ask you to find out the surface tension. The surface energy will be given. Next, the important is to find out the pressure intensity. Why? Because if I'm assuming that this is the droplets are there and the force is acting at a specific point, so there must be a pressure, like this is the force and this force is acting at this point, and it must be a pressure. So what about the pressure intensity? I need to find out that pressure intensity, because the pressure is always due to point of force, point force. So pressure intensity inside a droplet. So here I am going to assume that this the droplet is there, and the droplet radius I am going to assume that this is the d. Droplet radius is d. Diameter is d, and the radius is here r. I am assuming that. So let us consider the two parts of these droplets. Like when these droplets will get burst, if the pressure intensity and the force due to pressure is more than the surface tension force or cohesive force, then the bursting will occur. So I am assuming that here the two parts of this droplets. So there will be a two type of force will act. There will be a two type of force will act. One, the surface tension force that will always act on the circumference. You remember that surface tension always acts on the circumference, and the pressure intensity always acts on the cross-sectional area, and this is the pressure. So if I'll say here under equilibrium, the force due to pressure intensity, it must be equal to the force due to surface tension. So since we know that the pressure is equal to force by area, so the force will be equal to pressure into area. And also we know that surface tension sigma is equal to force per unit length. So F is equal to, we can say that sigma into L. You remember that this L is a circumferential length because surface tension acts on the circumference. It's a circumferential length. So P into the area is a pi by 4 d square, and the circumferential length is given as pi d. Pi get cancelled, 1d get cancelled. So the pressure is equal to 4 sigma by d. It's a Newton per meter square. This is the pressure. So this is the case for droplet, and the droplet have only one surface area. But if I'll say here, like a note, the pressure intensity inside a soap bubble. So soap bubble means it will have a two surface area, that is the inner one and the outer one. The pressure will act on the both the sided, Pi and P naught. So there's a two surfaces are there. So the total pressure intensity inside a soap bubble will be equal to 2 times of pressure intensity inside a droplet. It's a 4 sigma by 3. So P will be here 8 sigma by 3. It's a Newton per meter square because of two surfaces. Similarly, the next is the pressure intensity inside a liquid jet. Pressure intensity inside a liquid jet. The liquid jet is in cylindrical shape. That is a liquid jet. And I'm assuming that the liquid jet is length is L and the diameter is D. So if you assume that two part of the liquid jet, and if you cut it into the two parts, you will get it the shape. It will be look like that. It will look like that. If you cut it here, you'll get it here like that. And the thickness, I'm assuming that T here. The thickness I'm assuming at T. And the surface tension always acts on the circumference. And the pressure intensity always acts on the cross-sectional area. Cross-sectional area means this is the pressure here. So here also we say that under equilibrium, that P into A must be equal to sigma into L. So the area will be here pi d, The area will be here pi d, and sigma, the length of the circumference will be how much here? So it will be here, length of the circumference will be L plus L. It's a 2L. L plus L, it's a 2L. And the here circumferential area is a pi dl. No, it's a not pi dl, it's a only dl. Just a minute. It's a dl, and dl indicates that projected area. So this LL get cancelled. So the pressure intensity is equal to 2 sigma by d in a liquid jet. So whatever the questions they will ask you based on the pressure intensity. So we have all the formula we have derived that. That one formula is a P is equal to 4 sigma by d for droplet. You remember that. And P is equal to 8 sigma by d for the bubble. It's a hollow. And 2 sigma by d, it's for liquid jet. So any type of question is that you can solve it here based on that. Next, we will move it to the next capillarity. It's a very, very important capillarity. So capillarity means what? So if you assume that, let us consider this is the one container is there. And this container is filled with a liquid, and I'm going to immerse a small tube inside that. If you immerse it a small tube, there must be a rise of a liquid in a small tube. In a small tube, there must be a rise of liquid. So if you immerse a tube inside a container, there will be a rise of liquid. Or if you take out the small tube, there will be a fall of liquid. So rise or fall of a liquid inside a small tube when it immersed in a liquid is called a capillarity. It's called a capillarity. In a simple way, remember that rise or fall of a liquid inside a small tube is known as capillarity. So the rise is always occurs due to adhesion force. Remember that adhesion force. And adhesion force is always in water. Adhesion force. Adhesion force that is always in water. Adhesion force, and the water, in the case of water, there will be a rise of liquid. Why? Because of angle of contact is 0 degree. If the angle of contact is 0 degree, there will be a only rise here. Same way, the fall of a liquid is always due to cohesive force. And fall किस liquid में होता है? It is in mercury. In mercury, there is always a fall of liquid. Why? Because of only cohesive force are acting, not adhesive force. Because the mercury is non-sticky liquid. So यहाँ पे जो theta का value होगा, it's a 130 degree, and it's a more than 90 degree means it's a case for fall. So you can indicate it here for rise case and for fall case. Like this is the small tube is there, and if there is a rise is happening, there is a rise, so you can indicate it like that. And whatever the here circular section you will get it here, that is called meniscus. So if there is a water, there must be a rise. And why it is happening? It's due to adhesive force. Adhesive force is force between the different surfaces. The one there's a glass surface is there, and there is a one more a water surface is there. And cohesive force is always between the same surfaces. So that will happen in case of mercury. Mercury, if I'm assuming that is the mercury is there and this is the liquid is there, a mercury liquid is there. So there will be always a fall. It will always be fall. Why? It's a mercury is a non-sticky liquid. So you will get a meniscus. It will be like that. So whatever the angle of contact here, you'll get it here. Angle of contact. Angle of contact, it will be here more than a 90 degree. This is the theta. So theta is here more than 90 degree, and that is equal to 130 degree. And this is the theta, and theta is nearly, you will get it here 0 degree for water case. And for mercury case, it will be here 130. So next, I will write that capillarity rise. If there is a small tube is immersed in a liquid, then what will be the rise or what will be the fall? In both the cases, the expression will be the same here. So you assume that one container is there, and this container is filled with a liquid. And one small tube is immersed in that. So let us consider that the rise is h and the diameter is d. So I'm going to assume that here angle of meniscus is the meniscus angle or theta, its angle of contact. The sigma will always act on the circumference because this is the angle of meniscus. So along the circumference, the sigma will act. Sigma. So this sigma you resolve it. This side it will be sigma cos theta, and this side it will be here sigma sin theta. So here the rise is always occurs due to vertical component. Vertical component. So here under equilibrium, I will directly use the equilibrium formula. Rise of a liquid. If there is a rise, there must be a force. Which type of force is there? So that is the adhesive force. So rise of a liquid due to vertical component of a surface tension, it must be equal to weight of a liquid. So vertical component, how to find out? So the sigma is equal to, you know, that force by length. So force is equal to sigma into L. Use it here. It's a sigma cos theta because I will take it here vertical component into L. Yes, sigma cos theta into L must be equal to weight of liquid. It's a rho Vc because rho into volume is a mass, mass into G is a gravity force. Gravity force, it will act here downward, and that is a weight of liquid. Always act downward, and this force is acting upward. Now, rho volume is its area into height into G. So further sigma cos theta, and L is the length of the circumference. It's a pi d. Rho into area is a pi by 4 d square into height into h. So pi get cancelled, 1 day get cancelled. So here the h is equal to 4 sigma cos theta by rho g d. And this is the h4, that is a formula for a rise or fall case. In both the cases, it's the same. So when the tube is a cylindrical tube, if the tube is like a plates, so in that case, the formula will be different. You can drive it by the same way. So here, I can say that if theta is equal to 0, that is for water case, so the h value will be here 4 sigma cos 0 is 1 divided by rho 0. Or else, if you assume that theta is equal to 130 degree, so here cos 130 degree value you will get it here negative. So the H value indicates that minus 4 sigma cos 130 divided by rho GD, and this minus indicates that there is a fall of a liquid. So this formula is important here. So here the H value I got it here 4 sigma cos theta by rho GD. So if you look at here, the cos theta will be constant, rho will be also constant, G will be always constant. So the H value is always inversely proportional to diameter of the tube, dia of tube. So if the diameter of the tube is less, there will be a more capillarity rise. Or the diameter is more, the capillarity rise will be small. So the H is always inversely proportional to the diameter. Remember that this is the very, very important here. And the next, we will see the question based on that. So look at, we have a question number here, 15. If the diameter of a capillary tube is 1 mm, diameter is given here 1 mm. Just a minute. 1 mm. Then the capillary rise is 3 mm. Not 3 mm, it is a 3 centimeter. What will be the capillary rise? S2 is asking if the diameter changes to 0.2 mm. So no problem, we know that, since we know that H is inversely proportional to diameter, so H is equal to K by D. So if you write on the H1 by S2 must be equal to K by D1 divided by K by D. If you simplify that, it will be equal to D2 by D1. So the H1 value is given here 3 centimeter, S2 I need to find out. D2 is given 0.2 mm and the D1 is 1 mm. So the S2 value will be equal to 3 by 0.2. It will be equal to 13 centimeters. So here you can say that directly because here the diameter is decreasing here 1 mm to 0.5 mm. So once a 0.5 yeah, it means 5 times decrease kar gaya. So there will be a rise of liquid 5 times. So 5 into 3, it's a directly we can say that it's a 50 centimeter. So where is there? Only you need to remember the formula here. Next is find the capillarity rise in a pure water when the clean glass of diameter 1 mm is immersed in it. So we have a formula, the H is equal to 4 sigma cos theta by rho GD. So the sigma for water, you remember that it's a 0.0725 Newton per meter. This is the sigma value is there. And that substitute the value of sigma 4 into 0.0725 and the angle of contact is 0 degree for water case. Density is 1000 for water, 9.81, and the diameter it is given 1 mm, so 1 into 10 raised to minus. This 2 will get cancelled. So the if you simplify it here, the H value will get it here 0.03 meter or it's a 3 centimeter. So the answer is option number B is right answer. So if the data is not given for water case, if the surface tension is not given for water case, then we always remember that for water case it's a 0.075 and okay, so that's it is there. And remember that whatever the concept I had discussed here. So thank you everyone and please revise it everyone and revise everyone fluid properties. See that all the properties and this is the basic for fluid mechanics. Everywhere you need to use this data. Next, I will see that here static fluid. Under static fluids, we will discuss the pressure measurement, hydrostatic forces, and the buoyancy. There the 3 concepts are there under static fluid. We'll cover it in the next class. So thank you everyone.